Welcome to lecture 12. We are studying electronic devices and circuits, and from this lecture onwards, we'll be studying AC amplifiers. Before this, we have studied DC biasing techniques for BJT amplifiers for different configurations. An AC amplifier is based on a biasing circuit that we have already studied, except that the input is, in addition to the fact that the input is a voltage source which is AC, and the output is also AC and is used to drive a load RL. So the difference that we see in this circuit is that we have some additional components at the input and output side related to the AC. Precisely speaking, in general, an amplifier is a circuit whose input is a sinusoidal input voltage and the output is also sinusoidal. Input is an AC, output is an AC. It can be a voltage amplifier. Voltage can be amplified from input to output, or it can be a current amplifier. In this case, current is amplified at the output and voltage may not be. A fixed biased BJT amplifier is the one for which we have studied the biasing technique. This is the circuit we have already studied. This is a fixed bias configuration where we have analyzed and designed the circuit. In this lecture, we have added some more components. For example, C in, C out, the input AC voltage Vs, and the load resistor. This is a small input AC voltage that this amplifier will amplify at the output, and we'll see how. Before we talk about further about amplification, we'll see what this C in and C out transistors for. What are these C in and C out capacitors? C in and C out are input and output coupling capacitors. They are there because in this part of the circuit that I have embedded in this blue dotted box, we have both AC and DC, but we don't want DC to enter into a small input AC voltage source. The magnitude of this Vs, the input AC voltage source, is very small compared to VCC. We don't want this high valued DC current to enter into this source and destroy it. Likewise, at the output, we do not want this. Here we have, at the collector terminal, we have both AC and DC, but the output terminal across RL, we only want AC. So we have to stop the DC to the left of this C in, and we have to stop DC to the right of this C out. For that purpose, we have these capacitors, because we already know that capacitors block DC. So across Vs, we have only AC. Across RL, we have only AC. Where has DC gone? It has been blocked by the Cn at the input side and C out at the opposite side, at the output side. That is why we call these the coupling capacitors. So how does this circuit is analyzed for AC? How much will it amplify the voltage or the current? To analyze this, we'll apply superposition theorem. We already know that these transistors, diodes, all semiconductor devices, they are not linear. But for the sake of simplicity, and to analyze the theorems and laws we studied in circuit analysis, we have to come up with its linear circuit model. So we'll apply superposition theorem, and we'll replace this VCC with a ground, because we are analyzing only AC. So replacing this VCC with a ground. So what does this input side, and we track the path of AC current. The current leaves this Vs, flows through this C, and because this is AC, it can flow, and this terminal, it divides. A part of it becomes IP and flows through base emitter terminal, which is forward biased, and enters into the ground terminal. Another part flows through RB and goes to ground by flowing through RB. So on the input side, at the input side of this amplifier, we have a VS, and it says this capacitor appears to be short circuit for this AC, and then we have RB. RB goes to ground. This is VS. And then we have a parallel path whose resistance, the forward bias resistance of the base emitter terminal is RE. We'll study more about RE in our next lecture. It's a very small resistance, small RE. But we know that this small RE, once seen on the side, on the input side, that is the base, it multiplies with a beta. We have already studied that. Any resistance on the emitter side, any resistance on the emitter side, when seen on the base side, the input side, it multiplies with a beta. So we have this beta RE. And then on the output side, and this terminal is base. On the output side, we have the current IC, that is beta times IP. We already know that. The AC currents and AC voltages are represented with small letters, little letters. So we have a current source. As we know that emitter is grounded, and if this is the collector terminal, this is IC, which is beta IP, and flows to ground, and emitter is grounded, and the output current flows through RC. The output current IC goes to ground by flowing through the resistor RC, and at this terminal it goes to ground by flowing through RL, because RC and RL, they appear to be parallel to each other, because they're one of their ends are connected and the other ends are also connected and they are grounded. So they appear to be in parallel with each other. And this is RE. And one interesting factor is, and across this resistor RE, we have to find out the output voltage Vout. Another interesting factor is that through their combination, the current enters from the bottom terminal and leaves from the top terminal. That is why this configuration, common emitter configuration, is inverting in nature. In the lectures to come, we'll study about the voltage and current gain of these amplifiers. Voltage gain means the output voltage compared to the input voltage, the output AC voltage compared to the input AC voltage. This must provide some voltage gain, because common emitter amplifier provides both voltage and current gains, and we'll study about the current gain, the output current divided by input current. In the next lecture, we'll derive expressions for the voltage and current gain of this configuration, the common emitter configuration. Thank you.